Number one, during Hurricane Katrina, the atmospheric pressure or barometric pressure within the eye dropped to 27.33 inches of mercury. Express this pressure in each of the following units. Now, some of these units are on your equation sheet, and some are not. Now, I'm going to talk about kilopascals today, but you'll never see that on the AP exam. If it's not on your equation sheet, you will not see it on test or quiz, because you will not see it on the AP exam. Okay? So, and memorizing equations and constants, you don't do that. Don't do that. Okay? We don't need. You just have to know how to use it. All right. So we've got our barometric pressure, which is 27.33 inches of mercury, and we want to convert it first to millimeters of mercury. Do we have a conversion that will take us from inches to some metric conversion?
2.54 centimeters per.
And you don't ever need to know that, okay? We'll never use that in here on a test or a quiz. We'll use it for the homework. Okay, so we can convert the inches into centimeters. Okay. Now that mercury at the end tells us that we're looking at a pressure if you were to make a barometer. So 2.54, and then we want to convert the centimeters to millimeters. Which one's bigger, centimeter or millimeter? Centimeter. So we give it the 1, and how many millimeters in a centimeter? 10? Good. So 10 to 1, and whatever that equals. Anybody got an answer? $694, somewhere in that ballpark, and that is millimeters. All right, so just good old-fashioned conversions. Now, the next one, atmospheres, we will use. However, we'll start here. We won't start with the inches. Okay. So, if you wanted to show all the steps to get to atmospheres, you would redo that. Not going to do that. So we'll start off with the 694, or whatever number is still in my calculator. So millimeters of mercury. Is there a conversion on your equation sheet that takes us from millimeters of mercury to atmospheres? And if so, where would that be? Well, on the back side of your equation sheet, where the holes are on the right, you have your gases, liquids, and solutions. And your conversions are near the bottom right. 760. All right, so 760 millimeters of mercury in 1 atmosphere. So that's like less than 1. So divided by 760. Like 0.91. 3. Okay. And again, that conversion was on your equation sheet. All right. Letter C, a kilopascal. You won't find kilopascals on the equation sheet, but we'll do it today. The reason why I would show you some things, and I'll do this a couple times during the year, is that even though it's not on the AP exam, you may be exposed to it in college. So I don't want you to forget some of the skills that you learned in baby chem. All right, does anybody remember the conversion from atmospheres to, where are we going, kilopascals? Yeah.
So 101.325?
It is. And you don't need to memorize that, so don't be jealous. And KPA. So that's like, is that 90 something?
92.5.
92.5? And then the last one, torr. If you look on your equation sheet, we have 1 atmosphere, which we already used, is equal to 760 millimeters of mercury. Is there another conversion? Yes. Mercury? How much? Oh wait, we already have that one. Very good. So we also have on our conversion sheet this. So 1 millimeter of mercury is equal to 1 torr. So there's your answer for that one. So if you wanted to, just to be a phenomenal student, right, Danielle? You would do this. This just reeks of excellence. All right, let's look at number 2. It says the volume of a balloon is 485 milliliters when filled with 0.0222 moles of helium at a temperature of 20 degrees. What is the pressure of the helium atoms that are exerting on the sides of the balloon? We've got a pressure, a volume, moles, and a temperature. So we get to use PV equals nRT here. Now, if you want to, I'm not requiring you to do this, but if you want to, as an organizational type deal, you can always show the variables on the side that you know. Okay. Now, obviously, I'm not going to put R there since it's a constant, and your R is given on your equation sheet. We'll ask about that here in a moment. So the pressure is what we're looking for. It's a question mark. The volume is 485 milliliters. The number of moles is 0.0222 moles. The temperature is 20 degrees. Okay. Now, since we're looking for the pressure, and I'm not sure what you were taught or how you learned it, but for AP, we want to make sure that we isolate the unknown from the knowns. Okay. So since we don't know our pressure, but we know the volume, the number of moles, and the temperature, we want to move what we know to the other side. Okay. So I'm going to have my equation now look like this. All right, so here's what I did. And this, for those of you who had me in General Chem, you know what I'm doing here. But what I want to do is I want to isolate and get all of the known variables on the same side. So what did I do when I moved V from the numerator to the denominator? Yeah, I divided on both sides. Instead of showing the division on both sides, it's easy to remember that if I take a variable and move it or divide it by both sides, it's going to go on the opposite side. So if it starts in the numerator, it ends up on the denominator on the other side. What if I wanted to put V back on the other side? What would I do? Multiply it. So it would end up back in the numerator. Okay, so whenever you cross the equal sign, you move diagonally. Okay, doesn't always mean diagonally down, it means diagonal. So, and that's the easiest way to rearrange these. So I know my number of moles, I know my temperature, and I know my volume, and R is a constant. All right, so the moles, 0.222. The R, yeah, I'm sorry. We'll get there. You're jumping ahead. The R, which R are we going to use here? Look on your equation sheet. That'll be a dead giveaway. If you look on your equation sheet, again, there are some R values down here. Now, the very first R value that's listed, you have not used yet. That's a thermodynamics R. So, and how do you know it's a thermodynamics? Because it has joules, which we'll talk about much later. But the next one has the liter atmosphere mole Kelvin. That's the only R that we have for gases. So all of our pressures need to be in atmospheres. Very good. So we'll use the 0.0821 atmosphere liter. Now, some of you like to use multiple division lines. Do something like this. Okay. It doesn't drive me as crazy as it used to, but a cleaner way to show this, mole Kelvin is always on the opposite side of the value. So if you work with just one division line, okay, always keep the units mole Kelvin on the opposite side. So if R is down below, where will mole Kelvin go? It'll be on top. And it's really nice when you start rearranging variables and canceling out units that it's so clean. Okay. All right. Sonali, what do we need to do with the temperature here? 273.15. Where's that at on my equation sheet? Don't rely on that. Actually, it is on here. It's about the 5th or 6th one down. And what does it say? 273. So drop that 0.15. Yeah. In AP Chem, we don't care about the 0.15. So just add 273. And the reason why we don't care about the 0.15, it's insignificant. Okay. You're going to find out that 99.5% of our answers will have 3 significant figures in the final answer. So having 293.15, don't worry about it. So our temperature must be in Kelvin, and the reason why it needs to be in Kelvin, if we had a temperature of negative 20 degrees and we left it as degrees Celsius, what could that possibly give us for our volume? A negative volume. Wow. Think of the possibilities. If you could create negative volume, you would be rich beyond all means. Seriously, that would be amazing. So, I don't know, somebody might want to dream that up. Alright, never mind. Volume. Are we good with the 485?
No.
Why? Got to have liters. We have to have the same units. If we're using R, we have to have the same units. So 1 liter to 1,000 milliliters. Alright. This is painful, isn't it? Alright, so now that we have our things set up, let's cancel out any alike terms. And what are we left with? Atmosphere, which is pressure. See how clean that canceled out? Now we don't have to worry, is more on top or bottom? Well, if you put it on the opposite side of R, you're good to go. And that equals something. Anybody get an answer?
480.
No.
1.1.
1.1. And that is atmosphere. Now, what I am putting in the box, the box is the only thing that I would grade. Okay? So in other words, the variable that we're looking for, the variables that we know that have been rearranged, the values, and then the answer. So this is the minimum. How you get there is up to you. Okay? Some of you may need to show extra steps to get to this point here, and that's fine. There's nothing wrong with that. Okay, so, and then some of you might need to show this extra work just to organize yourself. That's fine, but this will never be graded.
Well, we need to put the labels on the answers as long as we know what corresponds with what. I mean, not the answers, the...
Within here?
Yeah.
Absolutely. Yeah, always show your units in every step. Okay. Number 3. When 5.27 moles of nitrogen gas is 745 millimeters of mercury at a volume of 2 liters is compressed to a new pressure of 300 kilopascals, what will the new volume be? Sounds like we have a before and after situation, which means we get to use PV equals nRT twice. Yay. And if you want to, you can do this, not requiring you to. Okay. But some might say, wow, that is awesome. Actually, I've never heard anybody say that in here. That is just beyond awesome. So you can put your variables that we know. Okay, the 1s are the before, the 2s are the after. And I'll typically do that just because I want to make sure everybody understands what we're doing here. So I have 5.27 moles to start off with at a pressure of 745 millimeters of mercury at a volume of 2 liters. Okay. And then it's compressed to a new pressure of 300 kilopascals. And it wants to know what is the new volume. Okay. Now, here's something that's interesting. I didn't say anything about the temperature. So what can we assume about the temperature? It stays the same. Okay. So T1 is equal to T2. And don't get your panties in a bunch. It's okay. We don't need to know what that temperature is. What about N2? I didn't mention anything about N2. Did I mess up?
That's what we're solving for.
Now we're looking for V2. I didn't say anything about the second set of moles. What did you say, Daniel? Or Emma? Stays the same. Good. If I don't say anything, then assume it to be the same. So we really don't care about that 5.27. It's what we call a distractor. Okay. And yes, on the AP exam, they're going to put something on there to go, what do I do with this 5.27? Nothing. Okay. All right. So actually what we have is a pressure volume situation. So we have a P1, V1, P2, V2. Now, again, what I want to do is make sure that all my initial sets, okay, my initial sets of variables are on the same side of the equal sign. Are they? Yeah. So the P1s, the initial set, we only care about pressure and volume are on the left side. So P2, V2 is also equal to nRT. Cool. Since nRT does not change, we don't care about it. So now we have P1, V1 is equal to P2, V2. Pretty P2, V2. Okay, so here's where we're at. And again, we're not even to the minimum point yet. Which variable am I looking for? V2. So I'm looking for V2, so that means P2 needs to go to the other side. Okay. So now I have my knowns on this side, and the variable that I'm looking for all by itself. Isn't that cool? So that really cleans things up. I mean, you don't have to worry about moving and cross multiplying. And cross multiplying is a bad habit. I don't know why they teach that to you guys. All right. We're not using R, so do we have to change the pressures in atmospheres? Correct. We don't have to change the atmospheres, but they must be the same. And since we're not going to use kilopascals very often, let's get rid of kilopascal. And does anybody remember how many millimeters of mercury are in 1 kilopascal? That was atmospheres in kilopascals. How many for millimeters? That's a long trip. Was it? Close, 7.5. Yeah. Hey, you're in the right ballpark. All right, so we've got 7.501. Trust me, I have very large ballparks. And if you're showing your work and your steps, I give you a lot of points. Because on the AP exam, it's the same way. They want to see your process. It's not always about getting the right answer. It's about showing the process. So let's get a number here. Sorry.
We've got 7.51.
That's a conversion.
Well, I mean, like, is it on here though?
It is not. That's why you're never going to have to worry about it after today. You may see it on the homework, but you won't see it on a quiz or a test. So I got 22. Whoops, just erased it. 2250. All right, so let's go ahead and plug these in. So I've got 745 millimeters of mercury on top. My initial volume was 2 liters, and my final pressure was 2250. Now let's think about this. If I'm multiplying variables, like multiplying pressure times volume, and if I have a before and after situation, if the pressure goes up, what should the volume do? Should it go up as well? It's inversely proportional. So anytime we multiply variables, they're inversely proportional from before and after. If, and again, this is in a fantasy world, if we had this situation, which we never will, okay, but if the pressure went up and we're dividing it, the pressure goes up, then the volume goes up as well. Very good. So they're directly related here, they're inversely proportional here. Okay? So some things to remember as you're working it out and you're saying, wow, it's multiplied together. So if my pressure goes from 745 to 2250, my volume should be going down. And would anybody get an answer for this? It's like 0.6 something, I think. 66? Okay. And that is liters. Good. Okay, so it's a quick check. It doesn't mean it's right, but at least it'll help you go in the right direction. And not that it's on the next question, but does anybody know what the pressure at sea level is? What is it?
1 atmosphere.
1 atmosphere. Good. Okay. Remember that. You might see that later on today. I don't know why. Might show up on the news. Might show up in your homework. Alrighty, number 4. Determine the temperature of a gas. Determine the temperature of a gas sample, oxygen, whose original volume is 4.55 liters at a temperature of negative 45 degrees, and its volume is reduced to 2 liters. Why do I erase all that? So we have a before and after situation. So that means we get to use PV equals nRT twice. 4.55 liters at a temperature of negative 45. And its volume is reduced to 2 liters. I want to know what's the temperature. Okay, so that's our set of conditions here. So our pressures don't change, and our number of moles don't change because I didn't say anything about it. And it is a very safe assumption that if we don't talk about it, it remains constant. And sometimes I may even say, hey, the pressure remains the same. Alright, so now we've got a fun situation. We've got a V1 and a T1. Okay? And a V2 and a T2. So, let's go ahead and get this started. We are looking for, T. We are looking for the temperature. So would it be best to move the T below or move the V below? Move the T? Yeah? Let's always try to make sure our T's are on top. So we'll move the V below. So now we've got this. Okay. If we're looking for temperature, we want to make sure it's on top. Now, we know T1, but remember that when we get done, the variables are going to look identical on both sides of the equal sign. All right, now we need to get N and R to the other side because they don't change. So now we've got this situation. Now we have the knowns on one side and the unknowns on the other. Actually, unknowns. No, we do know these. And these don't change. So since I have my initial set looking like that, my final set better look the same. Okay. P and R don't change. So now we've got this. Does anybody know what that law is or that equation? You'll never need to know it. It's one of those. Which is it? Charles. It's Chuck's law. States that as the temperature goes up, what happens to the volume? It goes up too. Good. All right, so we're looking for T2. Since we're looking for T2, what do we need to do to V2? Move it. So now we've got, here's our final, here's where I start grading. So T2 is equal to T1 times V2 over V1. Okay. So again, this is all prep work. It's optional if you need it. T1, what do we need to do that? Add 273, and what is that? 228, thank you. So 228, and then our volumes are good, excellent, so we don't have to change those. And 4.55. And so since the volume went from 4.55 to 2, what would we expect for the temperature to do? Go up or down? Go down. And I think that's 100. Yeah, that rings a bell. 3 6 Any questions? Awesome. Just remember that this right here would be the only thing that I would grade. Okay. Now, the reason again is because that's all AP or College Board is looking for. They want to see that you understand, hey, this is what we're looking for, this is what we are given or we know, and this is the work with the units and everything. Okay. And to be honest with you, there's some colleges that if you were coming in saying, hey, I got a 5 on the AP exam, they're going to say, you know, that's great. Here, take this real quick. Okay. And I've had a couple students come back and say, they didn't let me use a calculator. Which means that you were to show everything up to the answer. I really like that. Just think of all the problems you could do without a calculator. How sweet that would be. Calculator. No crutch. Alright, go ahead and work on the homework, sorry. Question number 1 is right here. And if you've seen it before, and I know that if you had me, I think I showed you guys this. Maybe. In other words, this balloon is inflated by the atmosphere. Yeah, the atmosphere is keeping this balloon inflated. Now, this is Shelby Adams' attempt at the same thing. And I guess a good question would be, why doesn't the balloon come out? I mean, there's water pushing down on it. I mean, I pull it down and it goes right back up. It's not magic. There's no magic in this room. Trust me. So it doesn't make sense. Why doesn't the water, like the balloon just pop out and the water fall into it? Why? Huh? Doesn't want to come out. A little bit will come out, and then it goes right back in. Just throwing that at you. We'll talk about it tomorrow, or whenever we meet again. When do we meet again?